All right, so get this. We're diving into the future of data storage today.
Wow.
A future where you could fit like the entire Library of Congress on something
Bro.
the size of a DVD.
Yeah.
No joke. We're talking 5D optical storage.
It's pretty wild.
And this research paper you sent,
Yeah.
honestly, it's got some pretty mind-bending stuff in it.
It really does. It's like storing information in a completely new way using light and these microscopic structures called nanogratings.
Nanogratings.
Yeah, it's like imagine etching tiny lines onto a piece of glass with a laser.
Okay.
Lines so small you'd need like superpowers to see them.
Right.
Those lines are the key to like unlocking this insane storage potential.
Okay, wait. Slow down for a second.
Yeah.
I'm all for microscopic superpowers and everything. But how do these nanogratings actually hold information? It's not like we're engraving tiny little letters on them or something.
Not quite. Think about it like polarized sunglasses.
Okay.
They only let certain light waves through, right?
Right.
These nanogratings are like custom-made polarizers. Each one twists light in a specific way, and we can read that twisted light to decode the data.
So it's less like writing and more like a secret code.
Yeah.
Based on how light interacts with these tiny structures.
Exactly.
But the paper mentions 5D storage.
Right.
I get the nanogratings, but where did the other dimensions come in?
It's all about layering and precision.
Okay.
We can layer these nanogratings on top of each other, creating a sort of microscopic skyscraper of data.
Whoa.
And by changing like the orientation and the depth of those layers,
Okay.
we unlock multiple dimensions of information in the same tiny space.
So instead of spreading data out on like a flat surface, we're building upwards and downwards too? That's some seriously efficient packing.
It is.
But the paper also talked about how these nanogratings are usually made.
Yeah.
And it honestly sounded like a pretty slow process.
It traditionally took dozens, even hundreds of laser pulses to etch each nanograting.
Wow.
This new research details a method using just 3 pulses.
3.
They're basically speedrunning the process by manipulating the laser's focus and energy.
3 pulses. That sounds more like a laser light show than data storage.
It's pretty cool.
But practically speaking, what kind of speed are we talking about?
We're talking about potentially writing data at speeds exceeding megabytes per second.
Okay.
Which means transferring entire movies in seconds. Say goodbye to download bars and hello to instant access.
That's incredible.
Right.
But the research used silica glass.
Right?
I hate to be the one to ask, but how durable is a data center full of glass going to be?
That's a fair point.
What happens if someone sneezes too hard?
That's funny.
Right.
But silica is just the starting point.
Okay.
The principles behind this technology could be applied to other materials too.
Okay.
And remember, we already use glass for long-term archival storage.
That's true.
Think about like ancient scrolls preserved for centuries.
That's true. Plus the paper hinted that this tech could mean data lasting even longer than that.
Right.
We're talking about a potential future where massive amounts of information aren't just easy to get to. They're potentially around for generations to come, like a digital time capsule.
Exactly. But to really understand how groundbreaking this is, we need to look at how these nanogratings actually form at like a molecular level.
Right.
Because it's not as simple as it sounds.
Okay, I'm always up for a little molecular adventure. Break it down for us. What's happening inside that silica glass when the laser hits?
So the first laser pulse creates what are called nanovoids.
Nanovoids.
Yeah, think of them like incredibly tiny bubbles.
Okay.
Formed by the intense heat of the laser. They're the building blocks for our nanogratings.
So they zap the glass, create a bunch of microscopic bubbles.
Yeah.
Then what? How do those bubbles turn into those neatly organized lines we've been talking about?
That's where things get really interesting.
Okay.
With the next laser pulse, these nanovoids begin to move and change shape. It's this delicate dance influenced by the laser's energy, the surrounding temperature, even the viscosity of the glass itself.
Wait, viscosity? Like how thick or runny something is?
Exactly.
I don't usually think of glass as a fluid.
You're right. We don't think of glass as a liquid. But at these incredibly small scales, the heat from the laser actually changes the viscosity of the silica right around those nanovoids.
Interesting.
It's like creating a tiny localized pocket of molten glass.
So they're essentially playing with molten glass at a microscopic level.
Pretty much.
No wonder it's taken until now to figure this out. But if these nanovoids are so sensitive to things like heat and viscosity,
Yeah,
that must make the whole process incredibly delicate.
it is.
What happens if the laser pulse isn't perfectly calibrated?
You're right, precision is key. Even the slightest variation in the laser's energy or focus can dramatically impact the final nanograting structure.
Wow.
That's actually one of the reasons this 3-pulse method is such a big deal.
Okay.
By precisely controlling each pulse, they've made the process significantly more efficient and reliable.
So it's like they've gone from using a hammer and chisel to a high-tech 3D printer.
Basically.
This is some next-level stuff. But speaking of high-tech, let's talk about accessibility. Right now, reading these nanogratings requires some pretty specialized equipment.
Sure.
Are we all going to need electron microscopes in our living rooms to watch a movie in the future?
That's a great question, and it's something that researchers are already working on. The good news is reading these nanogratings doesn't inherently require anything overly complex. Remember, it all comes down to how light interacts with those tiny structures.
So theoretically, you could develop a device that uses a more conventional laser to read those patterns,
right,
similar to how a Blu-ray player works today.
Exactly. In fact, the paper even suggests using this tech for more than just data storage.
Really?
Imagine microscopic sensors embedded in everything from buildings to medical implants.
Wow.
All capable of storing and transmitting vast amounts of information wirelessly.
That's a lot to process. We're talking about a world where data isn't just something we access.
Yeah.
It's woven into the fabric of our lives. But with that much data floating around, how do we even begin to think about security and privacy?
It's a critical concern. And it highlights just how important it is to develop really robust security measures alongside these advancements in storage technology. This kind of capacity for information storage brings with it a huge responsibility to make sure that information is protected.
Because with great storage capacity comes great responsibility.
Exactly.
But let's shift gears a bit. We've been talking about the potential applications of this technology.
Right.
But I'm curious about its limitations.
Okay.
The paper mentioned achieving a data capacity of up to 8 terabytes on a standard disk-sized piece of glass.
Yeah.
That's mind-blowing. But it's still a finite amount of storage.
It is.
Are there fundamental limits to how much information we can cram into these nanogratings?
That's where things get really interesting from a physics standpoint. There are indeed physical limits to how small and how densely packed these nanogratings can be.
Okay.
Light itself has a wavelength.
Right.
And you can't store information on a scale smaller than that, at least not with light as we currently understand it.
So even though we're talking about technology that sounds like something straight out of Star Trek,
I know, it's pretty wild.
we're still bound by the fundamental laws of physics.
Absolutely. But those limitations shouldn't discourage us. Remember, this technology is still in its infancy.
True.
What we're seeing today are just the first steps toward what could be a complete paradigm shift in how we interact with data.
And who knows? Maybe those limitations will lead to even more groundbreaking discoveries down the road. Maybe we'll unlock new physics that completely changes how we think about data storage. But for now, let's get back to the research at hand.
Okay.
We've talked a lot about how these nanogratings are made.
Yeah.
But I'm curious about the reading process.
Sure.
The paper mentioned something called retardance.
Right.
What does that even mean in this context?
Great question. Retardance refers to how much the nanograting slows down certain light waves compared to others. It's all about manipulating the way light vibrates as it passes through those tiny structures.
So each nanograting is like a tiny speed bump for light, slowing down some parts of the light wave more than others.
Yeah, like a filter.
And by analyzing that slowdown, we can decipher the information stored within.
That's pretty wild. It is. And it's that retardance combined with the nanograting's physical position that unlocks those extra dimensions of storage.
Okay.
Like we're adding floors to our data skyscraper, just like we were talking about.
Okay, that makes sense. I'm starting to see how this all fits together. But earlier you mentioned how this new method for creating nanogratings is much faster than the old way.
Yeah.
Can you unpack that a bit more? What's the secret sauce that lets them use just 3 laser pulses?
It's all about understanding the dance of those nanovoids.
Right.
Remember how I mentioned they gradually move upwards during the traditional formation process?
Yeah, like they're swimming towards the surface of the molten glass.
Exactly. That upward movement, while important in the traditional method, takes a significant amount of time.
Right.
And requires those multiple laser pulses. This new method bypasses that entirely.
Hold on. Are you saying they found a way to teleport these nanovoids into their final positions?
Well, not teleportation exactly.
Okay.
But it's pretty close. That first powerful laser pulse, the seeding pulse, creates the nanovoids right where they need to be, eliminating the need for them to slowly ascend. It's a game changer in terms of speed.
So instead of carefully guiding those nanovoids into position, they're basically saying, you know what? Let's just start with them exactly where we need them.
Pretty much.
That's brilliant.
It is. And with the next 2 laser pulses, the writing pulses,
Okay.
they can then refine the shape and orientation of those pre-positioned nanovoids. It's like the difference between like painstakingly arranging individual pixels to create an image and just snapping a photo with a high-resolution camera.
It's like they've cracked the code for instant nanofabrication. This is truly revolutionary stuff. But with all this talk about packing massive amounts of data onto tiny pieces of glass, it's hard not to think about the bigger picture. What does it really mean to be able to store information on this scale, potentially for thousands of years?
Wow.
It's almost a philosophical question at this point.
It is a profound thought, isn't it? Imagine future historians being able to access not just like the written word, but perhaps even recordings and images from our time preserved with perfect clarity for millennia. It really challenges our understanding of history and legacy.
It's like giving future generations a window into our world, a chance to understand who we were and what we valued.
Exactly.
What a gift and what a responsibility. But on a more practical level, this kind of storage capacity could revolutionize so many fields, right?
Absolutely. Think about scientific research, where massive data sets are becoming increasingly common. Or imagine entire archives and libraries accessible at your fingertips anywhere in the world. The possibilities are pretty much endless.
It's like the Akashic Records becoming a reality. But let's talk about the elephant in the room. With all this talk about storing information for thousands of years. What about the information we don't want to keep around forever?
Oh, like what?
Embarrassing childhood photos. Awkward teenage diary entries.
Oh, yeah.
Are we doomed to have our digital pasts follow us for eternity?
That's a very human concern. It raises important questions about data management and the right to be forgotten in this new age of practically permanent storage.
Right. It's not just about how much data we can store, but also about how we manage it, curate it, and yes, even delete it when necessary.
Right.
We'll need to develop entirely new ethical frameworks and data management practices for this technology. But that's a deep dive for another day. For now, I think we've covered a lot of ground.
Yeah, we have.
From the intricacies of nanograding formation to the mind-blowing implications of near-permanent data storage.
We've only scratched the surface, really. This technology has the potential to reshape not just how we store information, but how we interact with the world around us.
And speaking of scratching the surface, the research paper mentioned that they actually used this technology to encode text onto a piece of silica glass.
They did.
Tell me they didn't.
They did. They etched the text of the Book of Songs, one of the oldest surviving collections of Chinese poetry, onto a piece of silica glass about the size of a quarter. Imagine that ancient wisdom preserved in microscopic detail.
Wow.
Potentially outlasting us all.
Talk about a digital time capsule. It's incredible to think that something so small could hold so much history, so much culture. It really makes you think about the legacy we're all creating.
It does.
Both online and offline.
It does, and it begs the question, what will you choose to preserve and pass on? What stories, what knowledge will you entrust to this new era of data storage?
That's a powerful thought. And a perfect note to end on. It really makes you think.
It does.
This technology isn't just about like upgrading our hard drives. It's about preserving our collective memory, our art, our history on a timescale we've never even thought of before.
It's a lot of responsibility.
It is a lot of responsibility.
It
makes you wonder, like, what makes something worthy of being preserved for thousands of years? Who gets to decide that?
Right. It's like curating a museum, but on like a massive scale.
Right.
Makes you think, will future generations even care about our cat videos and memes?
Well,
or will they be looking for something deeper in our digital archives?
It's true. It makes you think. But let's bring it back down to earth for a second.
Okay.
We've talked a lot about the amazing potential of 5D optical storage.
Yeah.
Are there any downsides, any potential obstacles that might stop this technology from becoming widely used?
Well, one of the big challenges is going to be scaling up production.
Okay.
Right now, creating these nanogratings, even with this new 3-pulse method, is still a pretty delicate process.
Right.
And it requires specialized equipment. To make it commercially viable, we need to find ways to mass produce them.
Makes sense.
Reliably and affordably.
So it's not just about the science then?
No.
It's about the engineering and the manufacturing too.
Exactly. And then there are the economic factors to consider.
Right.
New technologies, especially ones that disrupt existing industries, are often expensive at first.
Of course.
Making 5D optical storage accessible to everyone will mean bringing down those costs.
It's always a balancing act. with new tech. The potential versus the practicalities. But if this research is anything to go by, the future of data storage is looking pretty bright.
I like what you did there.
I had to sneak a pun in. But you're right, there's still a lot to figure out.
Yeah.
A lot of challenges to overcome.
Absolutely.
But the potential is seriously revolutionary.
It really is.
And that's what makes this such an exciting field to watch. It's not just about small improvements anymore. It's about completely reimagining what's possible. And who knows? Maybe one day we'll be looking back at this conversation like it's from the Stone Age about this technology that changed everything.
It would be something.
It really would. But that brings us to the end of our deep dive into the incredible world of 5D optical storage.
It's been fun.
It really has. We've explored the science, the potential, the philosophical questions, even joked about our cat videos.
Hey, those are important.
Hey, I'm not judging. But most importantly, we want to thank you, our listeners.
That's right.
For joining us on this exploration of cutting-edge science and technology. Until next time, keep asking questions, keep exploring, and keep diving deep into the world around you. Okay, listener, buckle up, because today we're diving into the world of data storage. But not the kind you're used to. We're talking about storing data in glass.
In glass.
You heard that right, glass. You sent us this article, and it's a wild one, about something called 5D optical data storage, and it involves lasers.
Lasers?
Doing all sorts of cool things. Now, I'll be honest, when I saw words like femtosecond laser pulses and birefringents, I knew I needed backup.
Yeah, those are some technical terms for sure.
Expert speaker, are you ready to jump into this laser-filled world?
Absolutely. And this article is exciting. It's really a major leap forward in how fast we might be able to write data onto glass.
Okay, so before we get to that, can you set the stage? Why is everyone so interested in storing data in glass anyway?
It comes down to two things: longevity and capacity. The exciting thing about glass for data storage is it's incredibly stable. So unlike a hard drive that might crash or even flash drives that degrade over time, glass can potentially hold your data for thousands of years.
Thousands of years. So like I could leave a message for archaeologists in the distant future.
Exactly. And on top of that, we're talking about storing information on a scale smaller than the wavelength of light. That means incredible storage density. Imagine a disk the size of a DVD that could hold terabytes upon terabytes of information.
Wow, that's putting my external hard drive to shame. But you mentioned 5D data storage. Is this where things get a little, shall we say, back to the future? We're talking about storing alternate timelines?
Not quite. Think of it this way. We usually think of data as being stored in bits, which are like tiny switches that are either on or off, representing a 1 or a 0.
Right, like a light switch. On or off.
Exactly. In 5D optical storage, it's not just about a bit being on or off, but also its position within the glass and how it's oriented. Imagine instead of just writing on a flat piece of paper, you can write on microscopic layers within the paper, and you can even change the orientation of the letters.
Okay, so it's like packing way more information into the same amount of space.
Precisely. 3 of these dimensions are the physical position within the glass, like our X, Y, and Z axes. The other 2 dimensions are encoded in how these microscopic structures, called nanogratings, are etched by the laser. It affects how light passes through them. It's a bit like each nanograting acting like a tiny shutter, controlling how much light can get through.
Okay, so not time travel, but still incredibly complex and clever. This article is all about speed, though, right? They found a way to write data much faster using lasers. Can you explain what they did?
They did something pretty amazing. They achieved this with just 3 laser pulses.
3.
Just 3. And it all starts with a tiny bubble.
A tiny bubble. Okay, now you've got my attention. Tell me more about this bubble.
So the first laser pulse, they call it the seeding pulse, creates this tiny, we're talking nanoscale, bubble inside the glass. It's called a nanovoid, and that's our starting point.
So it's like a seed they plant in the glass.
Mm-hmm.
And then what happens?
This is where it gets really cool. Instead of just blasting the same spot with dozens of pulses like the old methods, they change tactics for the next 2. They shift the laser's focus and energy, and these they call writing pulses.
Mm-hmm. Okay, so they're not just hammering the same spot over and over again.
Yeah.
What do these writing pulses actually do?
They do 2 main things. First, by creating that initial nanovoid, they've changed the glass's viscosity right around that spot.
Viscosity.
Viscosity. Basically, it's a material's resistance to flow. So think about heating up honey. It becomes less viscous. It flows more easily.
Right, it gets thinner. Okay, so they're making the glass more malleable in that tiny region. What's the second thing they're doing?
The second thing is they're using near-field enhancement. It's a pretty neat trick. Basically, imagine you're using a magnifying glass to burn a leaf with sunlight, but instead of just one magnifying glass, you use several, and you position them carefully to focus even more light onto a single point.
You're really concentrating the sunlight.
Yeah, that's kind of what they're doing with the light in the nanovoid. These writing pulses actually interact with the nanovoid, and it amplifies their power right where they want to make the change.
So they're using the nanovoid to direct and intensify the laser light.
Mm-hmm.
That's some seriously precise work.
It is. It takes incredibly fine control. And on top of that, the researchers also had to account for something called the Kerr effect.
Kerr effect? What's that?
Intense light can actually bend slightly as it passes through a material. It's a tiny effect, but at these scales it matters. So the researchers had to adjust for that bending to ensure those writing pulses hit the nanovoid at just the right spot.
It's really amazing to think about all this happening on such a tiny scale. But they figured it out. They can write data with incredible speed using just these 3 laser pulses. So what does this mean for the future of data storage? Are we all going to be walking around with glass hard drives in our pockets soon?
It's definitely a step towards that, but it's probably not going to happen overnight. You see, this research dramatically speeds up the writing process.
Okay.
Reading the data back quickly and efficiently is another challenge altogether.
That makes sense. It's one thing to write a message in invisible ink, but you need a special light to read it back. What's the holdup with reading this data stored in glass?
Well, imagine trying to find and interpret those tiny microscopic marks and doing it at high speed.
Yeah, sounds tricky.
It requires really sensitive equipment and techniques, but researchers are working on new methods, so I'm confident we'll see a lot of progress there too.
So, glass hard drives might be a while off. But what about in the meantime? What's the most promising use for this technology right now?
Long-term data archival. Things that need to be stored really securely and for a very long time. Historical records, scientific data. Imagine a digital family archive that could last for generations.
Like a digital time capsule.
Exactly. And because glass is incredibly durable, it's very resistant to environmental factors. You wouldn't have to worry about things like humidity, temperature swings, or even magnetic fields ruining your data.
That's really incredible. It's like the ultimate time capsule for information. So, to be clear, if I wanted to send a message to the future, all I would need is someone with a really, really precise laser.
Well, it might not be quite that simple, but you're getting the idea. This technology really has the potential to change how we think about preserving knowledge and information for future generations.
This is all so fascinating. I'm already starting to imagine all these sci-fi scenarios. But before I get carried away, are there any limitations to this technology? Can we really store anything we want in glass?
It's important to remember that this is still an emerging technology, and like any technology, it has its limitations. One of the challenges is that we still need to develop different types of glass and optimize them for both storage capacity and for how fast we can read and write the data.
So it's not as easy as just etching something onto my drinking glass then?
Yeah.
Got it.
But even with those limitations, the potential here is just enormous. We've talked about writing data, we've talked about reading it back, but what about storage capacity? Is there like a limit to how much we can cram onto one of these glass discs?
Well, that's where things get really interesting and mind-bending, actually. You remember how we talked about 5D encoding, using the position and orientation of nanogratings?
Yeah, it's like packing data in all these different dimensions.
Right, exactly. Researchers are looking at ways to take that concept even further. Imagine increasing the number of states we can encode within each nanograting. It's like going from 5D to 6D. Or even higher dimensions of data storage.
Higher dimensions. Okay, now you're just messing with me, right? That sounds like something straight out of Star Trek. I know, it's pretty wild to think about. But it just shows the incredible potential of this technology. It seems like the more we learn about light and how it interacts with matter, the more we realize how much information we could potentially store.
That's amazing, but also a little daunting when you think about it. If we have the capacity to store that much information, how do we decide what to keep? What's important enough to preserve for potentially thousands of years?
That is a big question, and it's something that archaeologists and historians wrestle with constantly. But now imagine that question on a much grander scale. What if we could leave behind a record of our entire civilization, our knowledge, our art, our history, all for some future civilization to discover long after we're gone?
Wow. It's like a message in a bottle, but on a cosmic scale.
It really is. And I think it highlights how this technology isn't just about storing data. It's about preserving our collective memory, what we've learned, what we've experienced, and passing all of that on to future generations. It's about making sure that our knowledge and experiences aren't lost to time.
It's like building a bridge to the future, one laser pulse at a time. So, listener, as you go about your day, we want to leave you with this. What would you put on that bridge? What stories, what knowledge would you want to share with people in the future, maybe even thousands of years from now? Food for thought. That's it for today's deep dive. We'll be back soon with another fascinating topic, but until then, stay curious.
Ever get that like dreaded storage full notification? Drives you nuts.
Yeah. Tell me about it. It's like every time I turn around, I need more space for pictures, videos, files.
It's like our appetite for data is insatiable. But what if? What if we could store like tons of data, think movies, music libraries, all that, on something as small and like sturdy as a piece of glass?
Wait, seriously, glass?
Seriously, get this, we're diving deep into some wild new research about 5D data storage using things called femtosecond lasers.
Okay, hold up. Femtosecond lasers. That sounds straight out of Star Wars.
Right. But first, why this even matters. We all know the deal with hard drives, right? They're limited. And even those old school optical discs, they've got their limits too.
Totally. So this research, this could be huge for like the whole future of data storage.
Okay, back to these femtosecond lasers. The name alone sounds intimidating, doesn't it? Break it down for us.
Okay, imagine a pulse of light so short, so unbelievably fast, that you measure it in quadrillionths of a second. That's a femtosecond.
Quadrillionths. My brain just, like, short-circuited. Help me wrap my head around that.
Think of it like this 1 second compared to a femtosecond is like 0.32 million years.
Yeah.
Yeah, let that sink in.
Wow, okay. It's crazy fast. But why are these lasers such a big deal for, storing our cat pictures and spreadsheets?
It's about the precision. Imagine ditching a clunky chisel for like the most precise laser scalpel imaginable.
Laser surgery for data.
Exactly. We're talking manipulating matter at the nanoscale, the building blocks of everything.
So these lasers aren't just writing data, they're performing nanosurgery.
And get this, the material they're using is silica glass. Yep, the stuff of everyday windows.
Wait, what? Windows? That's even more wild. You're telling me my windows could be holding, the Library of Congress someday?
Well, maybe not yet. But within that ordinary glass lies the potential for some truly extraordinary data storage. And that's where this whole 5D thing comes in, right?
Yeah, 5D data storage. I'll admit, the first time I heard that, I totally thought we were talking about, parallel universes or something.
I get it. But it's actually not as crazy as it sounds. Imagine a cube that's your good old-fashioned 3D, right?
Right. Height, width, depth. Got it.
Now, picture etching tiny, super precise lines inside that cube using the laser. We call them nanogratings. The direction these lines are etched, that's your fourth dimension.
Okay, so we've got 3D space plus the direction of these tiny lines. So what's this mysterious fifth dimension, then?
Think of it this way. These nanogratings, they're like tiny speed bumps for light. They can slow down light waves that hit them in specific ways. The really cool part, they can control the speed bump effect with crazy accuracy, all thanks to those femtosecond lasers.
Okay, so they're basically creating a whole new language out of light encoded in these nanogratings. That's really freaking cool.
And this secret code, as you called it, can hold a mind-blowing amount of information. And because it's etched into glass.
It's got to be pretty durable, right?
Oh, you bet. We're talking about potentially storing data for centuries, maybe even millennia.
Data that could outlive the pyramids. Now, that's some next-level data preservation. But how do they actually write that fast? Wasn't there a bottleneck with speed before? It was like trying to write a novel with one of those old-timey single-tip pens, right?
Yeah.
Super slow, super tedious. So how'd they fix that?
That's where this research just blows everything out of the water. Imagine, right? The old way would be like hundreds of laser pulses just to etch one tiny little data letter.
Hundreds, just for one.
Yeah. And with this, they're doing it with just 3 pulses.
Wait, 3? Seriously, that's insane. How's that even possible?
Think of it like a 3-step process, a little dance, if you will. So first laser pulse, bam. This one's the most powerful. It's like a hammer.
A hammer. Okay, I'm picturing it. Go on.
It creates this tiny little dent, what we call a nanovoid. That's your starting point right there in the glass.
Okay, so pulse 1 sets the stage. What about the other 2? They tidy up or something?
Pulses 2 and 3, they're like the detail crew. They come in with less energy, very carefully calibrated, and they're focused just a tiny bit differently. Timing, energy, position, everything's got to be perfect. And they use that to shape the nanovoid into the nanograting.
So it's like They're sculpting with light. That's some serious next level stuff. But okay, I'm still a little fuzzy on how we get from nanogratings to, actual usable data. Like, is there some kind of nanograding dictionary I don't know about?
Think of it this way. It's all about how they orient the nanogratings, right? And that speed bump effect we were talking about.
Yeah, right. Red retardants.
Exactly. Combining those, they can store 4 bits of data in each tiny little voxel.
4 bits. Okay, that doesn't sound like much.
No, but think about how many voxels you can fit in, like a tiny speck of glass. It's an insane amount of information.
So you really could have, like, the Library of Congress on a piece of glass.
Potentially, yeah.
Yeah.
And because it's glass, it's crazy durable. We're talking about storing stuff for, who knows, hundreds of years, thousands even.
Data that could outlive the pyramids. That's insane. But, okay, hold on. How did they actually test this thing? Did they try storing anything on it yet?
They did. They started with something simple. The emblem of their university. Pretty detailed image, actually.
Oh, yeah.
Etched it right into the glass.
A high-tech school logo. That's one way to do it. But I'm guessing they didn't stop there.
Oh, no, they got way more ambitious.
Yeah.
They stored a digital copy of the Book of Songs. That ancient collection of Chinese poetry.
Wow. Okay, so we're talking about preserving, like, really important stuff here. Imagine if we had had this for, like, ancient texts and stuff.
Right. It's like a digital time capsule.
Yeah.
But let's get back to the speed thing, because we talked about how fast it is to write the data, but what about reading it back? Seems like it'd be a pain to decipher, like a code written in nanogratings.
Yeah, how do you even read something that small?
They use a special microscope. It analyzes how the light interacts with the nanogratings, which way they're oriented, how much they slow the light down, all that. And from that, they can decode it.
So it's like shining a light on a secret message and having it magically deciphered.
Pretty much. And get this. They estimate that with the tech we've got now, we could get write speeds up to megabytes per second.
Megabytes per second. So like downloading an entire movie in a few seconds, sign me up.
Exactly. And this is just the beginning, right? As the tech gets even better, those speeds are only going to get faster. Who knows? Maybe one day we'll have terabyte thumb drives, petabyte disks.
A world with no more storage full notifications. That's the dream. But I mean, this goes way beyond just like faster downloads or whatever, doesn't it?
Oh, absolutely. Think about the impact on, like, data centers, archives, heck, even things like medical implants. Storing a person's entire medical history on a chip the size of a grain of rice.
It's like something out of a sci-fi movie, but with, like, real-world implications. So out of all this, what do you think is the most mind-blowing part? What really blows me away is it's like we're watching science fiction become reality right in front of us.
Totally. Remember that Star Trek episode where they had, like, entire libraries stored on a little crystal?
Yeah. And now we're actually doing it, kind of. But it's not just about fitting more on a smaller device, right? It's the fact that it's glass. It could last, like, forever.
It's like a digital Rosetta Stone. Imagine our distant ancestors, thousands of years from now, unearthing this glass disc.
And suddenly, boom, they have access to our entire civilization's knowledge.
And think about how this tech could revolutionize, well, everything. Not just data storage, but fields like medicine, telecommunications, computing.
We're talking about a potential paradigm shift in, like, every aspect of our technological lives.
Exactly. And this is just with silica glass. Imagine the possibilities if we apply this technique to other materials. We could see data storage solutions that are even faster, even denser, even more versatile.
So the future of data storage is looking pretty bright and tiny. But this isn't just about the tech itself, is it? It's about how this could change our entire relationship with information, with knowledge.
Absolutely. Imagine a world without data loss. Instant access to massive amounts of information. A world where the physical limits of storage are practically non-existent.
Sounds amazing, but a little, I don't know, intimidating too.
Of course, of course.
Yeah.
Like with any powerful tech, we've got to think about the implications for things like data security, access, even potential misuse.
Those are conversations we definitely need to have. But for now, can we just appreciate how cool this is? This is some serious human ingenuity at work.
Absolutely. It's a testament to the power of, scientific curiosity and that drive to constantly push boundaries.
Well, we've covered a lot of ground today, from those mind-bending femtosecond lasers to the intricate dance of those 3 pulses to the incredible potential of 5D data storage. We've gone from cat videos to the Library of Congress, all in under 30 minutes.
Only on the deep dive.
And on that note, we'll leave you with this thought. In a world increasingly driven by data, how will this tech reshape our future? How will it change how we interact with information? It's something to ponder. Until next time, keep exploring the cutting edge.
Ever feel like we're reaching the limit of how much data we can actually store?
Yeah, it seems like every few years we just need more.
Like, remember when CDs were the big thing?
Oh, absolutely. Then DVDs came along, Blu-rays.
And now we've got the cloud. But even that has its limits.
Right, exactly. We're creating and consuming more data than ever before.
And it's not just about space, right? What about how long all that data actually lasts?
Totally.
Yeah.
Reliability is a huge factor. Hard drives crash. The cloud isn't foolproof.
So today we're diving into some research that could change everything. 5D optical data storage.
Using lasers.
Lasers to store information.
At the nanoscale.
Inside materials like glass. It sounds like science fiction.
It kind of is. This paper we're looking at has one of those titles that makes you do a double take.
Oh, tell me about it. Ready for this? It's called Rapid Generation of Birefringent Nanostructures by Spatially and Energy Manipulated Femtosecond Lasers for ultra-high-speed 5D optical recording exceeding MBs.
You sure you don't want to run through that again?
Maybe not. But don't worry, we'll break it all down. The key takeaway here is this research tackles that data storage problem head-on.
And it does it in a really fascinating way, addressing both capacity and longevity.
Which is where those femtosecond lasers come in.
Yeah.
So what exactly has a femtosecond laser?
Well, the femtosecond part is the real kicker. We're talking about ridiculously short pulses of light.
How short are we talking?
Imagine a quadrillionth of a second. That's 1 second divided by a million billion.
Whoa. I mean, I can't even...
Yeah, it's hard to fathom, right?
But what's the big deal with these super short laser bursts?
It's the precision they offer. Think about it. With these insanely fast pulses, you can interact with materials on a whole other level. We're talking about making changes at the nanoscale.
Nanoscale. As in smaller than the eye can see.
Way smaller. A nanometer is 1/1000th of a meter. It's like manipulating matter atom by atom.
Mind blown. So how does this laser wizardry actually store data?
Okay, so this is where it gets really cool. They're using these lasers to create what are called nanogratings inside the glass.
Nanogratings. Sounds like something out of Star Trek.
Right. But picture this. Incredibly tiny lines etched into the glass with these femtosecond lasers.
Okay, I'm picturing microscopic engravings. What makes these nanogratings so special for data storage?
It's all about how they interact with light. You see, these nanogratings are birefringent.
Birefringent. Okay, now you're just using big words to sound smart.
Huh. Fair enough. Think of it this way. Have you ever seen a calcite crystal?
Can't say I have.
Well, if you shine light through one, it splits the light into two beams. That's birefringence in action.
So it's like double vision for light.
Exactly. And these nanogratings, they do something similar. They manipulate light depending on its polarization.
Polarization, like polarized sunglasses.
You got it. So imagine controlling the orientation of these nanogratings and then shining polarized light through them.
You'd get different patterns of light coming out the other side.
Precisely. And by reading those patterns, you can store and retrieve information.
Okay, so we're not just talking about etching ones and zeros onto a surface. We're using light itself to store data.
You're getting it. And it's not just in 2 dimensions like a traditional hard drive.
This is where the 5D comes in, right? We're going beyond the 3 spatial dimensions.
Exactly. It's not about adding extra dimensions like in some sci-fi movie. Think of it as having 5 different ways to encode information within the glass.
Okay, break that down for me.
So you have the 3 spatial dimensions for positioning the nanogratings, but then you add 2 more dimensions based on the nanograting itself, its orientation, and how it affects that light polarization we talked about.
So it's like squeezing even more information into the same space.
Exactly. That's the beauty of it.
This is already blowing my mind, but I have to ask.
Yeah.
Creating these nanogratings, even with those super fast lasers, it's got to be a slow process, right? That's what I was thinking. It sounds like it would take like forever to etch all those tiny lines with the laser.
Right. That was a major hurdle, actually. Up until recently, creating these nanogratings was a pretty slow process.
So how did this research team overcome that speed bump?
Well, they found a way to drastically cut down the number of laser pulses needed to make each nanograting.
Drastically. How much are we talking here?
Instead of maybe hundreds of pulses per data point, they got it down to just 3.
3. Okay, now we're talking. How'd they manage that?
So instead of etching each line bit by bit, they came up with this 2-step process. First, they hit the glass with a really powerful seeding pulse.
Seeding pulse. What does that do?
It creates these tiny little voids inside the glass. Think of them like microscopic bubbles.
Okay, tiny bubbles. I'm following so far.
So then they use 2 more pulses, carefully calibrated writing pulses, to elongate those voids.
So they stretch those little bubbles into the nanogratings.
Exactly. It's like creating a blueprint with the seeding pulse, and then the writing pulses flesh out the design.
And because they're only using 3 pulses total, the whole process is much faster.
Exactly. And they can even control the size and orientation of the nanogratings just by adjusting the energy and focus of those writing pulses.
So it's fast and precise. That's incredible. But let's get real for a second. How does all this translate into something, useful for the average person? Are we going to be storing gigabytes of data on our sunglasses anytime soon?
Sunglasses hard drives might be a bit far-fetched, but the potential here is huge. Imagine never having to worry about your data degrading or becoming corrupted.
Wait, you're saying this could mean data storage that lasts for generations?
Think about it. Historical archives, family photos, important documents, all perfectly preserved indefinitely.
Wow. No more lost data because your hard drive failed. That's a game changer right there.
And it's not just about personal use. This technology could revolutionize data centers, making them way more efficient.
So faster data access, less energy consumption.
Exactly. It's a win-win all around.
Okay, I'm already sold on the idea of never losing another family photo. But this technology, it feels like just the tip of the iceberg. What else could this lead to?
Well, the researchers actually hint at something pretty interesting in their conclusion.
Oh, do tell. Don't leave me hanging.
So they were working with glass for this study, right? But they suggest that this laser technique, it might work on other materials too.
Now that's what I call food for thought. We could be talking about embedding data in practically anything.
Imagine the possibilities. Your phone case, a piece of jewelry.
Hold on, stop right there. A car window. A building facade.
Hey, don't let your imagination stop there. The point is, this could completely change how we think about data storage.
We're not just talking about smaller and faster anymore. We're talking about invisible and everywhere.
It's a whole new world of possibilities, all thanks to these incredible advancements in laser technology and materials science.
Mind, officially, blown. And to think, this is probably just the beginning. Who knows what amazing discoveries are just around the corner?
That's the beauty of science, isn't it? Always pushing the boundaries of what we thought was possible.
If you told me a few years ago that we'd be talking about storing data with lasers etched into glass, I wouldn't have believed you.
And in a few years, who knows what we'll be talking about then?
Maybe we'll look back on this conversation and think it was as quaint as, I don't know, a floppy disk.
I wouldn't be surprised. But hey, if you're eager to dive even deeper into the nitty-gritty of this 5D storage tech, we've got you covered.
We've got a link to the full research paper over in the show notes, so be sure to check it out.
And while you're there, let us know what you think about the future of data storage. Are we headed for a world where data is embedded in everything?
It's a question worth pondering. But for now, we'll leave you with that thought. Thanks for joining us on this incredible deep dive into the world of 5D optical data storage.
Hey there, deep dive listener. Ever feel like the world is generating more data than we could ever hope to store? I mean, between our digital photos, streaming services, and let's not forget those ever-growing research databases, we're practically drowning in information.
It's true. We are on the verge of a data storage crisis. Our current methods simply won't cut it in the long run.
Exactly. Hard drives fail. Cloud storage is vulnerable. And don't even get me started on how many times I've had to replace a worn-out thumb drive. But what if there was a way to store information that could last for centuries, even millennia, without degradation?
That's precisely the challenge that researchers are tackling with 5D optical storage in glass. It sounds like science fiction. But it's a rapidly developing field with the potential to revolutionize how we store data for generations to come.
Okay, so storing data in glass. That's a pretty wild concept to wrap our heads around. Where do we even begin?
The key to this technology is something called the femtosecond laser. Imagine a tool that can etch incredibly tiny, precise patterns inside glass. On the order of nanometers, that's a billionth of a meter. These patterns act like a code, storing information within the very structure of the glass itself.
So instead of ones and zeros on a hard drive, we're talking about microscopic engravings in glass.
Exactly. These engravings, called nanogratings, can change how light passes through the glass. By manipulating the orientation and size of these nanogratings with the laser, Scientists can encode information in 5 dimensions.
Hold on, 5 dimensions. That sounds a bit like something out of a Marvel movie. Can you break that down for me?
I hear you. It's mind-bending stuff. We're already familiar with 3 dimensions in space. Think of length, width, and height. Now imagine being able to add 2 more layers of information on top of that.
Okay, I'm picturing a box. I can see the length, width, and height. So what are the extra 2 dimensions we're adding to this box?
Imagine shining a beam of light through this box. The 4th dimension comes from the fact that these nanogratings can actually rotate the light's polarization. Think of it like twisting the light beam as it passes through.
Yes.
And we can control the degree of this twist. That's our 4th dimension.
Okay, so we're twisting the light. What about the 5th dimension?
That comes from controlling how much the nanograting slows down different parts of the light beam. It's a bit like adjusting the speed bumps on a road, causing some parts of the light to arrive later than others. This delay is the 5th dimension, and by adjusting the laser, we can fine-tune it with incredible accuracy.
So by manipulating these 5 dimensions within the glass, we can store information in a completely new way. But how do we actually write data onto these nanogratings? The paper we're diving into today unveils a groundbreaking technique for doing just that, and at a speed that was previously unimaginable.
Precisely. The traditional method of creating these nanogratings was a rather slow and tedious process, often involving hundreds of laser pulses for each bit of data. Imagine trying to chisel a detailed sculpture one tiny chip at a time. It would take ages.
Not exactly ideal when we're talking about storing massive amounts of information.
This new technique completely changes the game. Instead of slowly sculpting the nanogratings, they've developed a way to strategically seed the glass with tiny disruptions using a single, powerful laser pulse.
So it's like laying the groundwork for the engravings.
Exactly. They call this the seeding pulse. And it essentially creates tiny starting points for the nanogratings to form. Then they use just 2 additional laser pulses, carefully calibrated and positioned, to shape these seeds into the final information-carrying nanogratings.
So instead of hundreds of pulses, they've managed to create the same intricate nanogratings with just 3. That seems like a massive leap forward in terms of speed.
It is. This technique has the potential to increase writing speeds to megabytes per second. That's thousands of times faster than previous methods, and could make 5D optical storage a viable option for much larger scale data storage in the future.
Okay, this is where it starts to get really interesting for me. They've figured out how to create these incredibly precise, multi-dimensional engravings inside glass, and they found a way to do it much faster than ever before. But to really appreciate the significance of this breakthrough, we need to understand how these nanogratings actually form at the atomic level, ready to dive even deeper.
Absolutely. So we begin with a piece of fused silica glass, chosen for its exceptional purity and transparency. Now, when that high-energy femtosecond laser pulse is focused inside this glass, something incredible happens. The intense energy actually disrupts the molecular structure of the glass right at that tiny focal point.
So the laser is basically rearranging the atoms within the glass.
Essentially, this disruption creates incredibly small voids on the scale of nanometers, which we call nanovoids.
Nanovoids, so like microscopic bubbles within the glass.
You got it. They're incredibly tiny, but they play a crucial role in the formation of nanogratings. You see, with repeated laser pulses, these nanovoids act like magnets for the laser energy.
Okay, so I'm picturing a chain of these nanovoids forming along the path of the laser beam, kind of like a trail of breadcrumbs.
Perfect analogy. Now, as more laser pulses hit the glass, these nanovoids become more defined. They migrate upwards towards the region where the laser is focused, and they elongate, stretching out perpendicular to the direction of the laser's polarization.
Hold on, polarization, is that where our extra dimensions come into play again?
Exactly. We'll delve more into that in a bit. But you're on the right track. The key takeaway here is that by precisely controlling the laser's properties, its energy, its focus, and yes, its polarization, researchers can manipulate these nanovoids with incredible precision, essentially sculpting them into the desired nanograting structures.
So it's like a high-stakes game of microscopic billiards, using laser light to manipulate matter at the atomic level. Incredible. But how do researchers know what the right parameters are for the laser? How do they control the size, the shape, the orientation of these nanogratings?
That's where their research becomes truly groundbreaking. They systematically explored how different laser parameters affect the formation of nanogratings. They discovered that by carefully adjusting the laser's energy, they could control where those initial nanovoids form within the glass. More energy, deeper nanovoids, less energy, shallower nanovoids. It's all about finding that sweet spot where the laser interacts perfectly with the glass to create the desired effect.
So we've been talking about using lasers to etch tiny patterns into glass, and how that could revolutionize data storage as we know it. But you might be wondering, what does all this incredible science mean for me? What are the real-world implications of this technology?
It's a great question, and the potential applications are incredibly vast. Imagine a world where we no longer have to worry about data loss due to degrading hard drives or obsolete technology.
Right. No more scrambling to recover precious photos from a failing hard drive or trying to find a way to play those old CDs in the back of the closet.
Exactly. 5D optical storage offers a level of durability and longevity that's practically unheard of with our current methods. We're talking about storing information for centuries, even millennia, without any significant degradation.
That's mind-blowing. What would we even do with that kind of storage capacity?
The possibilities are practically endless. One of the most promising areas is long-term data archival. Think about all the irreplaceable information that humanity has accumulated over the centuries. Historical records, scientific discoveries, cultural artifacts. Right now, much of that data is stored on media that's prone to degradation and requires constant migration to new formats.
And there's always the risk of losing it all together due to accidents, natural disasters, or simply the passage of time.
Precisely. With 5D optical storage, we could create an incredibly durable and secure archive of human knowledge, ensuring that future generations have access to our history, our culture, and our scientific legacy.
That sounds like a game changer for museums, libraries, and archives around the world. Imagine being able to access documents from ancient civilizations or scientific data from centuries ago, all perfectly preserved in a piece of glass.
It's a truly exciting prospect, and it's not just about preserving the past. Think about the sheer volume of scientific data being generated today. From particle physics experiments to climate modeling simulations, 5D optical storage could provide a way to create a permanent and easily accessible record of this vital information for future generations of scientists.
So we've got a potential solution for the data storage crisis, a way to preserve information for generations to come. But what about everyday applications? Could we one day be carrying around 5D glass discs instead of thumb drives or external hard drives?
It's certainly within the realm of possibility. While current research is primarily focused on those large-scale archival applications, the potential for miniaturization and mass production is definitely there. Imagine storing your entire digital life photos, videos, music documents on a single, incredibly durable glass disc.
That would be incredible. No more worrying about your laptop dying or losing your phone. But let's be realistic. Every new technology comes with its challenges. What are the main hurdles that researchers need to overcome before 5D optical storage becomes more widely adopted?
One of the main challenges right now is speed. While this new technique we've been discussing represents a massive leap forward in writing speeds, it still has a way to go before it can compete with the lightning-fast read-write speeds we're accustomed to with solid-state drives and other modern storage devices.
Right. Nobody wants to wait around for hours to access their files. We live in a world where we expect information at our fingertips.
Exactly. But keep in mind, this technology is still in its early stages of development. The progress made in just the past few years alone has been astounding, so it's not unreasonable to expect even faster speeds in the near future.
Okay, so speed is one hurdle. What other challenges are on the horizon?
Another key challenge is cost. The equipment used to create these nanogratings, those incredibly precise femtosecond lasers, the specialized optics, it's all quite expensive right now.
Well, it is cutting-edge technology after all.
That's true. But as with any new technology, as research progresses and production scales up, the costs are likely to come down. It's just a matter of time and investment.
So it sounds like the future of 5D optical storage hinges on overcoming these challenges of speed and cost. What are researchers doing to address these issues and push this technology forward?
They're exploring a variety of avenues. On the speed front, they're experimenting with different laser systems, new pulse shaping techniques, even different types of glass to find that optimal combination for even faster writing speeds.
It's like fine-tuning a high-performance engine, squeezing out every last bit of performance.
Precisely. And on the cost side, they're looking for ways to simplify the manufacturing process, perhaps by using more compact and less expensive laser sources, or by developing new techniques for mass production that could significantly reduce the cost per unit.
So it's a two-pronged approach, tackling both the fundamental science and the engineering challenges simultaneously. What's really impressive is the level of collaboration happening in this field. You've got researchers from materials science, optics, photonics, data storage, all coming together, sharing their expertise. and pushing the boundaries of what's possible.
It's truly a global effort, and it's really exciting to see the progress they're making.
You know, we've talked about the potential applications of this technology, the challenges, the ongoing research, but there's something else I wanted to touch on, the sheer elegance of it all. Manipulating matter at the nanoscale with light, encoding information within the very structure of glass. It's both awe-inspiring and thought-provoking.
Absolutely. There's a certain beauty to it, isn't there? Using the properties of light itself to store information for potentially thousands of years. It really speaks to the power of human ingenuity and our endless curiosity to explore the unknown.
It makes you wonder, what will future generations think when they uncover this data, these stories preserved in glass? What will they learn about us, about our time, about the challenges we faced and the dreams we dared to dream?
It's a humbling thought, isn't it? To think that we have the potential to send a message in a bottle across time, a glimpse into our world, our lives, our hopes for the future. It really does capture the imagination, doesn't it? This idea that we might leave behind more than just crumbly ruins or faded photographs.
It's almost like a form of digital immortality, preserving a part of ourselves, our experiences, our knowledge, in a way that could outlast even the most durable monuments.
It really does. And it sort of begs the question, if we had the ability to send a single message to the future, encoded in glass, what would it be? What stories would we choose to tell? What discoveries would we want to share?
Would we focus on our greatest achievements, our technological marvels, or would we try to convey the essence of our humanity, our art, our music, our stories?
That's a good question. It would probably be a combination of both. A testament to our ingenuity and our creativity, our resilience in the face of challenges, and our enduring hope for a brighter future.
It's a profound thought, and it really highlights the power of information as a bridge across time. 5D optical storage has the potential to not only revolutionize how we store data, but how we think about our place in history, our legacy for future generations.
It does. And perhaps it also serves as a reminder of the importance of preserving our own history, our own culture, our own values, not just for the future, but for ourselves. Understanding where we've been can give us valuable insights into who we are today and where we might be headed.
Absolutely. So as we wrap up this deep dive into the fascinating world of 5D optical storage, I think we're left with a sense of both wonder and possibility. Wonder at the incredible ingenuity of this technology and the potential it holds for unlocking new frontiers of knowledge and preservation.
I agree. And the possibility of creating a more lasting and a resilient record of human achievement, of sharing our stories and discoveries with generations yet to come.
It's a future full of promise. And I, for one, am incredibly excited to see where this technology takes us next. Who knows? Maybe one day we'll be looking back at this very conversation preserved in glass for centuries to come.
Now that would be something.
It would. Well, on that note, let's leave our listeners with something to ponder. If you had the opportunity to encode a single message, a piece of your own story, onto a 5D glass disc, what would it be? Keep that question in mind as you go about your day, and we'll catch you on the next deep dive, where we'll delve into yet another fascinating topic shaping our world.